Hello everyone. I'm glad to present AP Chemistry 2022 free response problems. Let's work on problem number one. And I want to remind you that this problem has very similar setting and concept as in 2024 free response number one. So I already prepared this video, 2024 free response number one. I recommend you to look at that video too. Here in this problem, we are looking at acid-base titration, which is a very core concept in acid-base chemistry. And we have a triple objectives. First, stoichiometry. So understanding of balanced chemical equation and using that coefficients of balanced equation, converting, understanding mole to mole conversion, and theoretical yield. Theoretically, using that balanced equation, how much the product will be obtained at maximum amount. And percent yield, when you actually wet our hands to the chemical reactions, then actual yield is always less than theoretical yield because of competition reactions, because of loss of the reactants, because the reaction doesn't go to completion, you know, because of equilibrium those issues. Percent yield is always less than 100%. And in this problem is asking those issues too. And heating curve, we need to understand the heating curve. The usually in standard condition, room temperature, and I'm not room temperature, like this kind of 1 atm of atmospheric pressure. Solid is dissolving into liquid. Liquid is now vaporizing. Vaporizing at boiling point. There are certain exceptions, such as carbon dioxide. Dry ice is not directly going into gas. We call this a sublimation. Also, iodine. Iodine solid is now vaporizing directly into a gas, going through sublimation. Anyway, so let's think about how to apply the concept of heating curve. And number three is a common topic as we studied in 2024 free response number one problem. So number three is very important. So I want to put star mark here, star mark. This one, very important. How to read a titration curve. How to determine the equivalence point and the significance of half equivalence point. Why it is significant? Significant because the pH value at the half equivalence point is equal to pKa value of the weak acid used in titration. And concept of buffered solution, Henderson-Hasselbalch equation, pH is equal to pKa plus logarithmic value, the ratio between conjugate base concentration over acid concentration. Okay, so those things in mind, let's dive into working on this problem. So this problem is describing about methyl salicylate. Methyl salicylate is a reactant, and with the stoichiometric amount of the base, this one base is not specified in this problem, and it'll be leading up to a forming a carboxylate form, and after acidification step. So in the problem, it doesn't mention about what kind of acidification was used, but usually we are using hydrochloric acid, so I assumed hydrochloric acid was used, and the carboxylate will be protonated forming carboxylic acid. The final product is salicylic acid. This salicylic acid is a ingredient, a precursor to make aspirin, our anti-inflammatory non-steroid drug. So this reaction is frequently used in organic chemistry. Or anyway, so this is a process we are using to produce aspirin, part of the reaction. Okay, so now let's look at problem number one. Calculate. In the reaction, a student used 300 milligrams, 0.3 grams of methyl salicylate. Then calculate the maximum mass in gram quantity of salicylic acid. Okay. Here we need to understand what is the meaning of maximum mass. Maximum mass, in another word, this is theoretical yield. Theoretical yield. So this problem is asking us to find out theoretical yield of salicylic acid. So now let's write it out, what is given here. Or first, write the solution map. Solution map, factor labeled method is very useful in multi-step unit conversions. This is one of the problems. So we are given 0.3 grams of methyl salicylic acid. So then we are given mass in gram quantity of methyl salicylic acid. Let me write methyl salicylate. So salicylate. Okay. Let me write this one as methyl MS, methyl salicylate, and we are converting this one into grams. In order to use stoichiometry, you need to convert it into the mole number. Okay, stoichiometry is based upon the mole to mole conversion, so we need to convert this into mole number of methyl salicylate. And from here, now using the relationship here, the balanced equation is not given, but it is clearly said 1 mole. It is mole to mole conversion. 1 mole of methyl salicylate is converted to 1 mole of salicylic acid crystals. So then it is 1 to 1. So mole of salicylic acid. Once you know the mole number, then we can convert this into mass of salicylic acid. Mass in gram quantity of salicylic acid. Okay. So then first step is mass to mole conversion. So let's use molar mass. Molar mass of methyl salicylate. Then it is giving us conversion between mass and mole number. Mole to mole conversion is stoichiometry. It is given 1 to 1 conversion. And mole number of salicylic acid to mass. This one again, molar mass of salicylic acid. Okay. Now we are given, let's get started. We are given 0.3, excuse me, 0.3 grams. So let's get started from 0.3 grams of methyl salicylate. And we need to write 3 conversion factors. So those 2 molar masses and then 1 to 1. Let's choose a unit conversion. Let's get ready. This one to mole number. And then mole to mole ratio. And finally, mole to mass. So we need to convert grams of methyl salicylate to mole number. So let's write the unit first. And then using the molar mass, 1 mole molar mass is given 152.15 grams. Okay, so in order to reduce the amount of time used in calculation, the molar mass is given. Let's take the advantage of the given molar mass of methyl salicylate. And next, mole of methyl salicylate, we need to convert to mole number of salicylic acid. Problem clearly says 1 to 1, 1 mole to 1 mole ratio. And finally, mole number of salicylic acid to gram quantity, mass of salicylic acid. The molar mass is 1 mole as 138.12 grams of mass. Okay, then grams of methyl salicylate cancels out. Mole of methyl salicylate cancels out. Mole of salicylic acid cancels out. Now final unit is grams of salicylic acid. That's good. Grams of salicylic acid. And then simply plug in those numbers into the calculator. 0.3 times 138.12 divided by 152.15. It is 0.2723 grams. Let me underline 2. This is a last sigfig. So you can write this one as 0.272 grams of salicylic acid. Okay, so in the problem now, so this one is asking theoretical yield. So we need to set up always this type of, solution map, like starting from mass. Let me write it here. Always starting from mass to mass. Mass to mass conversion cannot be obtained in just one step conversion. We need to always go through mole to mole conversion. Remember, for a stoichiometry, for a mass to mass conversion, mole to mole conversion must be in the middle always. Okay, and then using stoichiometry. Stoichiometry is very useful in converting mole of one chemical species to another. Okay, and then let's move on to number B. Now 80% of yield is obtained, percent yield is obtained. Theoretically, we can obtain up to 0.272 grams, but after purification, we have now 87% yield. So actual yield is less than theoretical yield. So then one student suggested that some some salicylic acid sample was lost in rinsing with DI water, deionized water. So this one is consistent with the percent yield. This is asking. And properties of salicylic acid given melting point, solubility in water at 25 degrees C, specific heat capacity, and heat of fusion. Okay. So I was thinking about it. Oh, okay. So when you do this one, always what we do is using funnel here, and many times we do vacuum filtration. So one armed swan, and here vacuum, and we have funnel with solid, we have filter paper or filter right there, maybe the buccal filtrate or something. So then we put dry sample here. Always we need to rinse it. So we need to apply DI water, deionized water, and then rinse it. Okay. So then the solubility is given right there. Salicylic acid is soluble in water. So solubility is 2.2 grams per liter. Okay. So this one is 2.2 milligrams per milliliter. Let me multiply milli on both sides. Grams per liter is equal to milligrams milliliter because I multiplied milli on top and bottom each. Okay. So let's say we are using a small amount of water. Let's say 6 ml of water was applied for rinsing, and then 6 ml of DI water, and this is dissolving in 1 ml, 2.2 milligrams. I suppose this one, just I, to thinking about it. So this is 13 milligrams. So 13 milligram dissolved and went through the filter. It is not filtered, it went through the filter paper and, wasted out. It was lost. Okay, this is one thought. This is step one. When I was this one given, I had to think. And step two, I try to calculate the amount of the product. Okay, so point like 87%, 0.87, and our theoretical yield is a 0.2723 grams. Let's multiply it. This is how much? Let me calculate it. It is 0.237 grams. Okay, so theoretically we can obtain 0.272 grams, but 0.237 grams is actually obtained. This is actual yield. When you multiply the fraction of the percent yield multiplied by the theoretical yield, we can calculate the actual yield. Then difference is how much? This is 0.035 grams, which is 35 milligrams. Okay, so we have lost 35 milligrams. And when I was supposing 6 milliliters of water rinsing, and then when this is fully saturated with the salicylic acid, we are losing 13 milligrams. So when I was comparing like this way, and I was thinking, okay, it is possible. What the student said is consistent. Some of the sample might have lost. We can say may have been lost in rinsing stage, not totally 35 milligrams, but some of that might be lost in the rinsing step. So it makes sense. Okay, and then let's move up to the next problem. Okay, so then next problem is C. C is not giving us information, given information. And given the physical properties in the table, calculate the quantity of heat must be absorbed, increase the temperature of 0.105 grams of dry salicylic acid crystals from 25 degrees C to the melting point of 159 degrees C and melt the crystals completely. Okay. So this one is a heating curve problem. So 0.105 grams of salicylic acid at room temperature to completely dissolved. I mean completely melted at melting point. Melting point is 159 degrees C. Okay, find amount of heat required. Okay, so let's draw a heating curve. So heating curve is constructed like this way. So we're drawing on x-axis, y-axis right there. And what is drawn on the x-axis is the amount of heat applied. Amount heat applied. So we are heating more and more. So more and more heat is applied like this way. And what is on the y-axis is now temperature. Temperature of salicylic acid. Okay. So now let's get started. Initially, the sample was in 25 degrees C. It was a solid. This is degree C, solid. And as we heat it up more, the temperature will be increasing linearly. So let me draw a linear line. Linearly increasing. Okay. So because the specific heat is a constant at this region, and heat up it is increasing linearly, and as it reaches the melting point. So let's say the melting point is given 159 degrees C, 159. As it reaches the melting point, the temperature doesn't increase. The applied heat is used to melt this compound. And then as it is completely melted, then from that point on, it becomes liquid. And in the liquid, the temperature is increasing again like this way with different specific heat. Okay, so then our interest is this area. We are heating up to raise the temperature solid. Here we have a solid, the temperature is increasing, and then as the temperature reaches melting point, and solid and liquid, the solid is started to melt. So start melting, and melting completed. Complete melting. Complete. Okay. All right. So then we need to have two regions of calculation. First, in a solid region, we need to raise the temperature from 25 degrees C to melting point. And then second, we need to calculate amount of heat completely melting the solid. So then we have two regions. First region is here. Here, this region for Q1, amount of heat. And in this region, until it is completely melted, it is Q2. And we have different equations, formulas. Okay, Q1 is now we are raising the temperature of solid. In this case, we are using MC delta T, MCAT. When we are raising the temperature of a substance in the same phase, we can use MCAT. Okay, so first mass is given how much? It is 0.105 grams. So let me use a ruler to calculate, this one. Okay. And then what is the specific heat? 1.17 joules per gram Celsius given. So when you have 1 gram of salicylic acid to raise the temperature 1 degree C, it requires 1.17 joules of energy. And we need to calculate delta T. Delta T, we want to raise the temperature from 25 degrees C to 159 final from 25 degrees C. So this one is 134 degrees C. Okay, then let's write it here, 134 degrees C. Now let's take care of the units. Grams divided grams cancelling out, degrees C cancels out. We are finally left with joules. So this one is joules. And how much is it? Let's calculate it. it is 16.46 joules. And underline 4, 3 sig figs. So in the third sig fig, let's underline, but keep more number because this one is not a final calculation. In Q2, this one, the temperature doesn't increase at all. And in this time, when it's melting or boiling, we have to use latent heat. Latent heat. Heat of fusion is given here. Heat of fusion is given how much? Heat of fusion is given 27. Okay, let's go to the table. Heat of fusion is given 27.1 kilojoules per mole. So we need to use this information. Currently, gram is given, but the heat of fusion is molar value right there, molar value. So we need to convert grams to mole first, and let's multiply this value. So then this value is, we have 0.105 grams of salicylic acid. Now raise the temperature to the melting point 159 degrees C, and let's convert this one to mole number using the molar mass of salicylic acid. 1 mole has 138.12 grams of salicylic acid. Now we are ready. Grams of salicylic acid cancels out. It is converted to mole number, and 27.1 kilojoules of energy required to melt 1 mole of solid. So then mole cancels out, and finally the first one is given in joules unit. So let's convert this to joules. 1 kilojoule is 1000 joule. So kilojoule cancels out. So this one is 20.6 joules. Okay, so then total amount of heat, Q total heat is raise the temperature from 25 degrees C to 159 degrees C, and then we need to use melt the total amount. Okay, then it is 16.46 joules plus 20.6 joules, which is 36. First, it is 37, let me raise it, okay. It is 37.06, and finally 37.1 joules. So this is the final value. Okay, so in this problem is asking us to understand how to construct a heating curve, and from the heating curve, can you calculate the total amount of energy required? Here we need to divide the region into 2 regions. First one is solid region, single phase region. Second one is a double phase region. Solid is started to melt, but not completely yet melt. So this region, number 2. And number 2 region, here, let me go back. Number 2 region and solid and liquid and mixed. We cannot use MCAT equation, Q equals MCAT. Instead, we have to use the latent heat, which is heat of fusion in this case, 27.1 kilojoules per mole, and then add up. Total amount of heat is not total. So raise the temperature of solid to 159 melting point, and then from melting point we are dissolving it. Okay, now let's move up to next problem. Next problem, D is asking, let me see. Okay, D is asking about comparison of the intermolecular force, dispersion force, dipole, and hydrogen bonding, and explain why the melting point of salicylic acid is now much higher than that of methyl salicylate. Okay, so methyl salicylate is a structure is like this one. We have benzene ring, we have a ester group, and here methyl, and this one is alcohol. This is methyl salicylate, and salicylic acid structure is benzene ring. Benzene ring is common, and here it is carboxylic acid. It is also hydroxyl group. So this is salicylic acid. So melting point is -9 degrees C melting point. But here this melting point is now much higher, 159 degrees C. So in room temperature at 25 degrees C, methyl salicylate is present as a liquid, but salicylic acid is a solid. Okay, how can you explain this physical property difference using intermolecular forces? All right. So in order to find out intermolecular forces, when you think about polarity of a molecule, this is a the the atoms at the central position, we have many multi-atoms. Then when you think about locally and focusing on the functionality, okay? So what I mean is focusing on this ester and hydroxyl group, and then again hydroxyl group and this carboxylic acid. And now let's compare left hand side, right hand side. They have both benzene ring, same functionality, hydroxyl same functionality. The only difference is methyl salicylate has ester, and then salicylic acid is not carboxylic acid. The ester was transformed into a carboxylic acid in a chemical reaction by entrainment with a base. Okay, so this one has ester has only, this is polar bond, and it has dipole force. Okay, that's the major intermolecular force present. I mean, it caused by the presence of this ester. What about carboxylic acid? So carboxylic acid, let me write it alkyl group and carboxylic acid right there, oxygen and hydrogen like this way. Hydrogen like this way. Let me draw another molecule of carboxylic acid and inverted position. Here it has carboxylic acid right there, and then right there. Okay, alkyl group. All right. Here, please note there is a strong hydrogen bond. Okay, this oxygen has a lone pair, and this hydrogen is strongly partial positive, partial negative. So then there is a hydrogen bond. Hydrogen bond between carbonyl oxygen and the alkyl hydrogen. The hydrogen in the hydroxyl group, hydrogen bond. And again, second hydrogen bond is present right there. This one, and with this hydrogen. So we have double hydrogen bonding is present in for carboxylic acid. That's why carboxylic acid usually has high boiling point, high melting point. So the difference between this high, like large difference in the melting point is explained by the double hydrogen bond present between the molecules of salicylic acid. This is missing in methyl salicylate. That's why there is a large difference. Now let's move on finally to titration. Here, titration. Student titrates 20 ml of 10 millimolarity of salicylic acid with 20 millimolarity of sodium hydroxide, and then using a pH probe to monitor the pH of the solution, the data plotted producing the following titration curve. Okay, so this is a curve. So this problem is very similar. First, let me write it here. This is very similar to 2024 free response problem, FRQ question number 1. At the time we used lactic acid. Lactic acid also has hydroxyl group. This is 3-carbon compound. Lactic acid is a 3-carbon compound. It is carboxylic acid and alcohol like this way. So this problem and 2024 problem, the difference is we have now benzene ring instead of this methyl group. It is very similar problem. And then titration is asked. So titration is not very important concept. When you learn general chemistry, we need to know about the interpretation of the titration curve. So let me put two star sign right there. Okay. All right. So this one is asking, using the information in the graph, estimate pK value of salicylic acid. So we need to we need to first understand, we need to determine the what is it? The equivalence point. Okay, equivalence point. Here, initially the pH value was low, and then let me follow low, and then as you add sodium hydroxide more, it is slowly increasing, pH increasing, and suddenly it is jumping to a high pH region, and then the middle, approximately the middle value is this one, is the equivalence point. So let's go down. At equivalence point, the pH is now abruptly increasing. So this is the equivalence point. This is the equivalence point, and this is the amount of volume, amount of sodium hydroxide used. It requires 10.0 ml of sodium hydroxide to reach the equivalence point. And then half equivalence point is very important. So half of 10 is 5. So then let's go to 5 and go up. And this one is half equivalence point. Half equivalence point is very important because the pH value, let me read pH value right there. The pH value is same as pKa value. So this one around this equivalence point is a buffer region. The solution initially not a buffer. When it reaches equivalence point, it is not a buffer, but close to in the vicinity of the half equivalence point, the solution becomes, the amount of the concentration of HA, weak acid, is conjugate base A negative, weak base. Their concentration are comparable, so this becomes buffer solution. In buffer, we can use Henderson-Hasselbalch equation. pH is now pKa value of weak acid plus logarithmic value of weak acid concentration under conjugate base concentration at equilibrium. Okay, at half equivalence point, initially we have only here we have acid only, HA only, and when you add hydroxide, sodium hydroxide more and more, HA is converted to A negative, and here at half equivalence point, the concentration of HA becomes equal to concentration of A negative, the conjugate base. Why? Because half the amount, this is a half equivalence point, meaning half the amount of weak acid is converted to its conjugate base. So this becomes pKa plus log of 1. We know that log 1 is 0. So then at half equivalence point, pH becomes pKa. pKa is a constant, but pH is a variable as you add more and more of sodium hydroxide. As you saw in this graph, it is increasing steadily and suddenly jumping to a high value. Okay, so then let's estimate. When I estimate, the pK value is at 3.1. We cannot write up to second decimal. The pH is given only increasing of 1, so we can estimate up to first decimal. My estimation is now 3.1. When I read this value, 3.1. Okay. Now, and problem F is asking, and try to gauge your level of understanding in interpretation of this titration curve. When the pH of the mixture is 4.0, is there a higher concentration of the weak acid or its conjugate base in the flask justify? Okay, so we can do many things here. Let's do different methods. Method 1, let's look at this pK value. Let's go to the graph. Okay, and then draw a horizontal line from the 4 horizontal line until it is intersecting with the titration curve, and it is intersecting around here, around 8 or 9 milliliters of volume. Okay, so then we know that at pH is around 4, pH value 4, meaning volume of NaOH, how much? around 9 mil added. Was added or is added. Okay. So that let's have quick quantitative calculation. I want you to understand the quantitative calculation. And here we have zero point 0.2 moles per liter of sodium hydroxide. Okay. So we figured out the volume of sodium hydroxide used to reach pH 4 is approximately 9. We don't need to have a very accurate value. Approximation is good enough because we are doing estimation for quantification. So we had initially 20 ml of 0.01 molarity salicylic acid. I wrote as HA, as monopyrotic acid, and titrate with 9 ml of 0.02 molarity sodium hydroxide. So let's calculate the mole number. First, initially we have 20.0 mil and 0.0100 molarity is moles per liter, and this is same as millimoles per milliliter. So for titration, we are using small quantity in the lab, in our lab scale. So then it is useful to write the moles per liter as millimoles per milliliter. So it is millimoles per milliliter. So then milliliter cancels out. This is 0.02 millimoles. So initially we have 0.02 millimoles of salicylic acid present. Now the sodium hydroxide concentration now 0.2 molarity, 0.02 molarity, correct? 0.02. Let me see. 0.02. Okay, so 0.02 molarity, which is 0.02 millimoles per milliliter. Okay, so then let's multiply 9. 9 mil times 0.02 millimoles of sodium hydroxide per milliliter is equal to milliliter cancels out. It is 0.18 millimole. Oh, I have a miscalculation. Sodium hydroxide was added. This calculation right there. This is not 0.02. This is 0.20. 0.20. Okay. Okay. Right there. 0.20. All right. Okay. Then let's set up a stoichiometric table. This is not an ice table, stoichiometric table. So salicylic acid, let me write it as HA. It is reacting with sodium hydroxide and consumed. It is forming water. So Na, salt and water. And let me erase actually. So hydroxide, sodium ion is a spectate ion. So let me focus on net ion equation. And let me use millimoles. So before the reaction, we have only 0.2 millimoles of sodium hydroxide, and this one was added 0.18 millimoles added. Okay, and then we didn't have zero amount of conjugate base, and then the liquid water is formed, but water is solvent, so we do not write the amount of water. Change, and after the reaction. So then 0.18, this is strong base, 0.18 millimoles, this is completely consumed in 0.18, and 0.18 is generated. So after the reaction is over, we have only 0.02 millimoles remaining, sodium hydroxide completely gone. We have 0.18 millimolarity. So then as you see here, the conjugate base is now much more, 9 times more at this condition. So I just calculate to show you that actually it is much more. And then we don't need to calculate up to here. Method 2. Method 2 is simply figuring out the volume. So here, this is amount of sodium hydroxide from 0 to 10. So this is the volume of sodium hydroxide added. This is equivalence point. 0 is initial, 10 is equivalence point, equivalence volume. Okay, and then 5 is half equivalence point. And remember, initially we have HA only. And at the equivalence point, we have A only. The conjugate base only. 100% of HA was converted to the conjugate base. And then at half equivalence point, we have HA concentration is equal to A negative concentration. I mean the conjugate base concentration. So then as you see here, when you add sodium hydroxide more and more, conjugate base concentration increasing, and so the acid, salicylic acid concentration decreasing. So here initially from 0 to half, initial to half equals point, the acid concentration is more than conjugate base. But as it passes the half equals point, now HA concentration becoming smaller than conjugate base concentration. So that 9 is this region. So then this is our answer. And then above, I showed quantitatively why, how much of the A negative concentration, conjugate base concentration more than HA concentration. So method 2 is good enough for this problem. Now let's move up to finish this problem. G. Benzoic acid is very similar in its structure as salicylic acid. Salicylic acid has OH hydroxyl group. Hydroxyl group is missing for benzoic acid. Ka value in 6.3 times 10 to the negative 5. Calculate pK value of benzoic acid. Remember P function, whatever it is, pH, pOH, pKa, pKb, is defined as negative common log of Ka value. This is the definition. Remember, P function is negative log. So we simply plug in negative log, Ka value is given. 6.3 times 10 to the negative 5. Here, plug in this one into a calculator. And when you write the answer, you need to think about the suffix. Here, 2 suffix. And when you write the answer, the number of suffixes is now reflected to translated into a number of decimal places. So the value is 4.20, 2 decimal places. Okay. And usually it is a good idea, even though we are not sure about the suffix. In pH and pK value, we are usually writing up to a second decimal. Okay. Now let's move to the final problem. Titration of 20 ml of 10 millimolarity benzoic acid. Compare with the original one. So then the volume, the concentration is exactly the same. Original one is 20 ml of 10 millimolarity of salicylic acid. In this case, it is benzoic acid. Compare with the original titration curve. Okay. So then let's compare. Half equivalence point, the value was 3.1, I estimated, but now in this case it is 4.2. So then and half equivalence point, benzoic acid is higher pK value. So then let's write it here, 4.2. Okay, 4.2, and benzoic acid is then slightly high. So then follow is always higher above the line like this way. But because it is monoprotic acid, both of them monoprotic acid, and their concentration volume exactly same, then their equivalence point same. So at equivalence point, it is the pHs are going up, and at the base level here, they are overlapping with each other. Why? Here NaOH is dominant. NaOH is an excess reagent when it passed the pH. So initially the pH level of benzoic acid is slightly above the pH level of methyl benzoate, I mean pH level of salicylic acid, but as it passes through the the equivalence point, then at that point they are all converted into conjugate base, and it is now sodium hydroxide is excess amount in dominant. So then the the pH level is overlapping. So here in this problem, what the authors want to see is, do you understand at the half equivalence point? So pKa value is pH, so then should be above. This one is benzoic acid curve, and the bottom one is salicylic acid curve. Okay. So in this problem, we saw also again another titration example. As I said in the beginning, titration is so important. 2022, the major problem in free response is about titration. In 2024 again, after 2 years, we see very similar problem. So then make sure, so when you prepare for the upcoming a AP exam, so then review this problem, 2022 number one problem, 2024 number one problem again, and blank without looking at those things, just yourself try to figure it out, and then after that one and compare your answer with this video. And I hope this video be becoming helpful in preparing your own preparation, I mean exam. I will see you next time.